Earlier in the course, we classified equilibrium solutions of differential equations and used these classifications to understand the long-term behavior of solutions near the equilibrium solution. For linear systems of differential equations, we'll also study and classify equilibrium solutions. We define an equilibrium solution of a system of differential equations y prime of t equals a times y of t to be a solution y of t such that y prime of t is the zero vector. In this case, where y prime of t is the zero vector, we have that 0 equals y prime of t equals a times y of t. And thus our equilibrium solutions satisfy the equation 0 equals a times y of t at all values of t. And for any value t equals t naught, the linear system of equations 0 equals a times y of t naught is just a linear system of equations, not differential equations. And it has a unique solution so long as the determinant of a is non-zero. And it's easy to check that y of t naught equal to the zero vector is a solution, since a times the zero vector equals the zero vector. And thus it is the unique solution in this case where the determinant of a is non-zero. So for all linear systems of differential equations, y prime of t equals a times y of t, where the determinant of a is non-zero, the only equilibrium solution is y equals the zero vector, which in the phase plane is the origin. So in the phase portrait, the equilibrium solution is a point at the origin. Now that we know the point at which the equilibrium solution occurs, let's look at how to classify it. We will classify the equilibrium solutions based on the behavior of nearby solutions. Now, if both straight line solutions, and thus all of our solutions, go out of the origin, we call the equilibrium solution a source. We saw an example of this in our very first phase portrait that we got from the direction field. And if both straight line solutions, and thus all solutions, go into the origin, we call the equilibrium solution a sink, which we saw an example of in our last example. And finally, if one straight line solution goes into the origin and one goes out of the origin, we call the equilibrium solution a saddle point, which is the phase portrait we saw in the second example. So notice whether we have a source, a sink, or a saddle point depends on if our straight line solutions are going in or out of the origin. But whether the straight line solutions are going in or out of the origin depends on the signs of the eigenvalues. So we can classify equilibrium solutions just from the signs of the eigenvalues. In the first case, where we have a source, lambda 1 and lambda 2 are both positive. When we have a sink, lambda 1 and lambda 2 are both negative. And finally, in the case where our equilibrium solution is a saddle point, one of our eigenvalues is positive and one of our eigenvalues is negative. These three cases are all of the types of equilibrium solutions we can have as long as the matrix A has a determinant that is non-zero.